Good day. From Global Surgery's Johannesburg Hub in South Africa, this presentation has specifically been recorded for the NIHR Global Surgery Unit's training platform. I am Deirdre Kruger, Associate Professor of Surgical Research in the Department of Surgery at the University of the Witwatersrand. And this presentation is entitled Basic Biostatistics, Introduction to Basic Statistics in Biomedical Science. Briefly, what I will cover in this presentation is what statistics can and can't do, continuous variables versus our categorical variables, and what do we do with these variables, descriptive statistics and/or inferential statistics, such as associations and correlations. And throughout my presentation, I will summarize by using examples. So what can statistics do? It can certainly provide objective criteria for evaluating a hypothesis. It can summarize and synthesize information from your data. It can facilitate the detection of patterns in your data and also therefore suggest a relationship or lack thereof. And it can enable you to critically evaluate a hypothesis or argument. What it can't do is tell the whole truth. It can only give you probabilistic conclusions. It cannot compensate for poor study design, in particularly underpowered studies. And it can't indicate clinical significance, although clinical significance can only follow statistical significance. So firstly, let's talk about categorical variables. Now, these can either be ordinal or nominal. Ordinal or ordered categorical variables have order, such as disease stage, 1, 2, 3, 4, Apgar scores, and even a Likert scale. Whereas nominal categorical variables include examples such as gender, blood type, and race. Now, categorical variables are usually reported as frequencies and proportions, and certainly nominal variables are always reported in this way. Ordinal categorical variables, however, may sometimes be reported as means. So let's look at numerical or continuous variables. These can either be discrete, such as visit numbers, study visit numbers 1, 2, 3, and 4, they always follow each other. You can't have visit number 3 without having 1 and 2. Same with goals scored in a match. Whereas continuous numerical variables include things like blood pressure, weight and height measurements, age, as well as biochemical measures. Now, these continuous variables are reported as a mean with standard deviation, or if your data is not normally distributed or non-parametric, we will be reporting them as median with an interquartile range. So of course, there are different graphical representations of our data. So for categorical variables, it's nice to display our data in pie charts or bar or column charts. Here's an example of eye color in a population according to the pie chart. This bar or column chart is showing us the categories of color for M&Ms in a bag of candies. Continuous graphical representation can take different forms. We can also use a bar column chart, and this will be specifically appropriate if you've actually categorized your continuous variable, such as in this example, age, which is a continuous variable, has been categorized according to different age categories of youth, young adults, all the way to the elders. Box plots are really nice for summary statistics, and you'll see that the middle line always represents the median, whereas the box represents the interquartile range. And then, of course, the minimum and the maximum of the range are also calculated as the whiskers. We can also use line plots to display our continuous variables, such as in this example, it's data over time. And then we have a scatter plot. Scatter plots are what we use, and on these we usually calculate our correlations And these really usually are when we are displaying two continuous variables against each other. So what are descriptive statistics? So this is a statistical method for organizing and summarizing your data using numbers, tables, and graphs. So this is the scale of measurements of the data, and it really measures the central tendency of your data by means of a mean, a range smallest to largest, a middle value, such as the median, or the mode, which would be the most frequent value. So again, for categorical data, our descriptive statistics include frequencies and percentages, whereas for continuous data, we measure location. And this depends on whether the data is normally distributed or not. But then around the measure of location, we measure variation in forms of standard deviation, range, or interquartile range. And again, we use these descriptive statistics to then graphically summarize our data. What about inferential statistics? So this is a statistical method using a sample or a small group to make an inference or to draw a conclusion of the population as a large group. So inferential statistics uses probability to determine how confident we can be that the conclusions drawn from the sample or the subpopulation are correct to extrapolate to the greater population. We use confidence intervals to also report this data, as well as margins of error. My apologies. The choice of statistical test depends on whether your data are categorical or continuous. So of course, whether it's categorical or continuous, we want to know, are you comparing two groups, such as those who have received a surgical intervention versus those who have not? Or more than two groups, such as if we're looking at the mechanism of injury, was it penetrating, blunt, or did it fall into the third category of other? Also, this depends on whether you're looking at continuous versus continuous data. Like I said, this is usually when we have a scatter plot, and continuous versus continuous is when we refer to correlation. For the rest, we are talking about association. So I would like to refer you to this reference listed here at the bottom, this Petrie paper on statistics in orthopedic papers. This is a freely accessible manuscript that really shows all these figures that I'm showing you now. Nice, just almost cheat sheets for how to know which test to use. So please go and fetch them there and keep them on file. It's really easy to follow. So for example, categorical data. If we've got a categorical variable that we're looking at, for example, gender, we're comparing it in two groups. Again, those who received a surgical intervention versus those who did not. So this will then tell us, okay, if these patients in our sample population are independent, which they usually are in clinical medicine, and probably the type of studies that you'll be looking at, you'll have two independent groups. So then a chi-square test will be applicable. The Fisher's exact test we apply when there are small numbers in our data. What are two groups that are related? So this will be a categorical variable, for example, stage of disease in a patient over time. So it's related because there are two time points for the same patient. So the time points are related to the same patient. And in this case, different statistics will be applied. If you're looking at more than two groups, again, you will use the chi-square test, but this will show you a trend because unlike in this first arm where you would have a one pairwise comparison, so a true 2x2 table, when you're looking at more than two groups, you'll have a 2x3 table or a 2x4 table or a 3x4 table. And then your chi-square test will really just show you trend. So you may be advised, and I'll show you examples soon, where you can combine your groups to make 2x2 tables, a one pairwise comparison to actually see where does that p-value from the chi-square test or the Fisher's exact test, where does it actually apply? So this is our one for continuous variables, what tests we use when we're analyzing continuous variables for inferential statistics. So again, these are numerical or ordinal variables. If we are again comparing two groups, so two categories, those that received intervention, those that did not, but we're looking at a continuous variable such as age or shock index. Again, the patients are independent unless you have follow-up longitudinal data, which would be related. But in an independent cross-sectional study, you will use the two sample t-test, specifically if your data is normally distributed. Your continuous variables, such as age, if it's normally distributed, you will use the t-test to compare those who've been intervened versus those who have not. If your age is not normally distributed, you will be looking at a non-parametric test. And in this case, comparing two groups, it's the man-Whitney. If we've got more than two groups, we'll use the ANOVA, but if it's non-parametric, we'll be looking at the Kruskal-Wallis test. So what about continuous data? I've discussed this before, continuous versus continuous variables. Again, if your variables are normally distributed, you will use a Pearson correlation. If they are non-parametric or skewed, you'll use a Spearman correlation. So I keep talking about whether your data is normally distributed. So yeah, we're talking about your continuous variables. And this is when there's a strong tendency to take a central value. And you'll see that you'll have this really nice bell-shaped curve in a normally distributed variable. And in this case, the mean, the median, and the mode will be approximately equal and divide this curve exactly in half. So much so that the distribution is perfectly symmetrical or almost perfectly symmetrical, and all standard deviations on both sides of the mean are the same. So you will see that 68% of the values fall within one standard deviation of the mean, 95% of all observations fall within two standard deviations of the mean, and 99% of all your data fall within 3 standard deviations of the mean. So this is our normal distribution for which we'll apply our normal statistical inferential tests such as the t-test and the ANOVA. So again, in our normal distribution, the mean, the median, and the mode are all the same, or approximately the same. If our data is non-parametric or skewed, you'll see that our perfectly shaped bell-shaped curve is now skewed. And if this is skewed to the right, our median will be lower than the mean. If our data is skewed to the left, our median will be higher than the mean. So in this case, it's important to not report the mean, but rather the median and the interquartile range. So for my examples in this presentation, I'm going to use an example data set of a real master's study that we conducted in our department. The study was looking at shock index and injury severity score as prognosticators of emergency surgical intervention and in-hospital mortality in level 1 trauma patients. So the population in this example data set, it was a retrospective cohort review of all trauma patient records at a single academic tertiary hospital trauma unit, which was modeled after a level 1 trauma center in the US. Data was collected over a 1-year period, and all patients were over the age of 18. So let's first look if data is normally distributed. And in this example, our first research question is, does shock index on arrival differ by gender in level 1 trauma patients? So this is to test if the independent variable of gender causes an effect on the dependent variable of shock index. So when you take data in an experiment, the dependent variable is the one being measured. And in this case, it's shock index. So as I've said before, to know what tests to use, you need to know if your data is normally distributed. So how do we determine if our variables are normally distributed? So as I showed you on the bell-shaped curve, the mean and the median will be the same. So if they're the same, you know it's normal distribution. But what if you're not sure? And this is when we can apply a statistical test to see if our data is normally distributed. And we, more often than not, use the Shapiro-Wilk test for normality of data. And the Shapiro-Wilk test p-value greater than 0.2 will indicate a normal distribution. So if we look at our patient population, you'll see in this example data set, there is 1,943 patients, 89% of which were male and 11% of which were female. Now, I've given you shock index as a mean and a median. And like I said, to know if data is normally distributed, the mean and the median are the same. So we know that shock index is very sensitive and a 1 unit change makes a massive difference. So if we just look at the mean and the median across the categories, we see that it does not look the same. But again, in the case of female, you may think 0.78 and 0.73 are actually quite similar. So this is why we run the Shapiro-Wilks. And again, if this p-value is greater than 0.2, it indicates a normal distribution. In this case, you can see it's nowhere near 0.2. And therefore, we can use non-parametric statistics because our data is not normally distributed. So I'm going to go to Stata to just show you how this test was conducted. So here we are in Stata, which is a statistical suite of analytics software. Specifically, Stata version 16 is what I currently have. I've already imported the data sheet, which was an Excel data sheet. The variables you can see are all here on the right. I've just also loaded my commands for ease and for time. But I'll show you in any way initially, your nice drop-down menus where you can find whatever it is that you need, especially if you know what you need from those cheat diagrams that I've given you. So there's summary statistics, means, proportions, frequency tables, with or without measures of association, classical tests of hypotheses such as your t-test, non-parametric, Kruskal-Wallis, your correlations. But we now want to look at the distribution of shock index in this population. So as I said, we test for normality using the Shapiro-Wilks test. If you know the command, you don't have to go this route. So we want to look at shock index and we want to look at it by gender because that was our question. But let's first just look at the group as a whole. So you can see the command was SWILK, so Shapiro-Wilk for shock index. The 1,943 patients were all included. And you can see that the p-value as displayed on my table earlier is nowhere near 0.2. So again, when we are looking at data according to categories, we also need to see what they look like in their separate groups. So we're going to repeat the command by our group independent variable, which is gender. Now you'll see it's by gender, sort, Shapiro-Wilks shock index. And you'll see in the females, again, p-value nowhere near normally distributed, neither are the males, but actually if you just look at the variance, and you'll remember that the females, the mean and the median were much closer together, and in this case, the variance, you can also see that for males, it's much higher. You can also look at this, if we look at the graph, again, it looks quite normally distributed, but then you can see it really is skewed to the right. If we look at the females, again, as we saw, the mean and the median were more similar compared to the males, but still skewed to the right. And in the males, which quite represents the curve for the entire population, it's because 89% of this population were male, but you can see that the data is in fact not normally distributed. To also just show you that if we summarize shock index in our population, again, we've got 1,943 patients or observations. The mean was 0.71 and the median, which is the 50th percentile, is 0.67. And this is what I displayed in my table that I showed you. Here we have the standard deviation of 0.28, and we have an interquartile range from the 25th to the 75th percentile of 0.55 to 0.80. We can also tabulate gender. So again, we summarize shock index because it was a continuous variable, but gender is a categorical variable. So again, we will be reporting frequencies and percentages, and these are the percentages that you saw in my table. So if we summarize shock index according to gender, you'll see that in females, yeah, we have, again, like we said, similar median and mean, and an interquartile range. But then for males, we can see that the shock index was 0.66, the median, versus 0.73 in females. So it seems like there's a difference. We know our data is non-normally distributed, so we're going to use a non-parametric test to actually see, but does this 0.66 in males differ significantly from our females? Again, you may see that it looks like it, you may think it does, but again, we apply statistics to make these assumptions. So back to our first research question. Does shock index on arrival differ by gender in level 1 trauma patients? So this is what we looked at to determine the normality of the data. Now we know it's not normally distributed. We're looking at a continuous variable of shock index in gender, which is 2 groups, male versus female. These are independent samples and they are non-parametrically distributed. So we need to apply the Mann-Whitney U-test. Okay, so again, even though we know our data is not normally distributed, which really does tell you to report your median and your interquartile range, there is an exception where if each individual subgroup has an N number greater than 30 and the variance is not significantly different, you may in fact apply the t-test. So we may apply the t-test, but we are also going to use the Mann-Whitney test just to err on the side of caution. But nevertheless, the fact that it's not normally distributed, regardless of the numbers per group, says you're reporting the median and the interquartile range. So again, let's go to Stata to run these tests and see, is there a significant difference between male and female with regards to shock index? So back in Stata, again, you can use your drop-down menu if you don't know if you don't know the command. I know that the command for Mann-Whitney is the rank sum, because the Mann-Whitney and the Wilcoxon rank sum test is actually the same thing. So we are looking at shock index by gender. So again, it ranks it because it's not normally distributed. So you needn't worry about all of this. What you're looking at is the p-value, yeah. And you can see that there's a significant difference in shock index according to gender. As I said before, we can use the t-test because our observations in each group is more than 30. So if we look at the parametric test by gender, again, we're going to look at the one that doesn't assume any specific direction. And you see that the p-value is still super significant. So regardless of which test, Mann-Whitney or t-test, there's a significant difference in shock index between our males and our females. So to answer our question, you would have seen the p-values were 4 zeros in Stata. So we then always make it 3 zeros and a 1. And the t-test was a 3 zeros and a 2 p-value. So the question, does shock index on arrival differ by gender? Yes, significantly so. Okay, let's look at when we are comparing more than 2 groups. So our question is similar, but now we're asking, does shock index differ on arrival by mechanism of injury in trauma patients? So again, we're going to apply the Shapiro-Wilks test to see if these differ. And our 3 groups, so comparing more than 2 groups, are penetrating trauma, blunt trauma, and other. So other would include those that did not specifically fall under these categories. And because it made up almost 7%, we decided to include them, even though many publications only compare penetrating versus blunt. So again, our whole patient population is in here, 1,943. When we look at the mean and the median shock index, again, for all patients, it would be the same as with gender. And then when we look according to mechanism of injury, we can see that again, there is a difference. This data is not normally distributed, and from the Shapiro-Wilks p-value, which you now know how we get in data, our data is certainly not normally distributed. So therefore, let's see what tests we need to apply. So in our continuous data again, because shock index is a continuous variable, but this time we're going to the right because we're comparing more than two groups that are independent patients and it's non-parametric distribution. Therefore, we will be applying the Kruskal-Wallis test. Okay, so let's go to Stata. Okay, so again, we did the Shapiro-Wilks, which showed our data was not normally distributed. When we summarize shock index, as you saw in my table, we have it for blunt, for other, and we've got it for penetrating. And if we look at it, 0.67 for blunt is the median, 0.65 and 0.67 again for other and penetrating. So we really do need to apply statistics to know if there is any significant difference. As we said, we need the non-parametric Kruskal-Wallis test, which I know that this is the command by mechanism of injury. And yeah, you can see this is just all the rank sum information of the test, which you needn't bother yourself with. What we want to know is what is the p-value, and here it is, 0.44. So clearly, it seems that it is not normally distributed, that it's not significantly different. So does shock index on arrival differ by mechanism of injury? No. P-value 0.44. So what about categorical data? So we had shock index as a continuous variable, but what if we're comparing to categorical variables, such as, is the mechanism of injury associated with a need for emergency surgical intervention in level 1 trauma patients? Okay, so mechanism of injury, we know, had 3 categories, and emergency surgical intervention is literally, did you have intervention, yes or no? So that's a 2-category variable. So you'll see here, a part of course from the total columns, we have a 2-by-3 table. Okay, and you can see the percentages in penetrating. 71% of penetrating trauma were not operated on, compared to 90% and 91% in blunt and other respectively. Okay, so we've got a categorical variable. It's more than 2 groups that are independent. So we're going to do the chi-square test to look for trend. And then we may combine our groups to actually have a 2-by-2 or 1 pairwise comparison to then again do a chi-square or Fisher's. Fisher's is applied when there are small numbers in subgroups, because then from the 2-by-2, we can clearly see where the p-value lies, where yeah, we can just talk about a trend. Okay, so is the mechanism of injury associated with a need for emergency surgical intervention in trauma patients? You can see here from the Pearson Chi as well as the Fisher's, it is significantly different. So again, we can see that 28% of penetrating trauma required emergency surgical intervention, compared to only 9.8% of blunt and 9.3% of other. So we can say that there's a trend that penetrating trauma requires significantly more emergency surgical intervention compared to patients with blunt or other trauma. But now again, as I mentioned before, sometimes you want to regroup so that you have a nice 1 pairwise comparison or a 2-by-2 table. So in this instance, we will combine category blunt and other. So we will still have our total patient population of 1,943 patients. And if we do combine them, this is what it looks like. And again, you'll see that penetrating trauma, 28% as it was before, compared to only 9.7% in any other mechanism of injury patients. So again, our tests, our Pearson chi-square and our Fisher show that this is significantly different. Okay, but maybe if I can just quickly show you how to run this statistic in Stata, so you know where it's come from. So yeah, we are tabulating our categorical variables. So we're tabulating mechanism of injury according to emergency surgical procedure. And we're looking at row, column percentages, and we're applying the Pearson chi-square and the Fisher's exact. Okay, so just if you want to look at this key, the top entry in the table is the frequency, followed by the row percentage, and then the column percentage. And these are obviously the entries that I had on my table in PowerPoint. And again, usually it will give Fishers if it feels like you need to use Fishers. It may be because some of the categories have rather small numbers. But again, yeah, we can talk about a trend because it's a 2x3 table. But as I said, we're then going to look at mechanism of injury where we combine, when we're combining anything else that's not penetrating. We run the same statistic. And you now see we've got a 2x2 table, but we still have our entire patient population of 1,900. Okay, so we won't use the one-sided Fisher because that's if you had a power calculation up front in a clinical trial. So we are using this p-value here. So it's 0.001. There's a statistically significant difference in the need for emergency surgical procedure in penetrating trauma compared to any other mechanism of injury. Okay, so as I said before, we combine these to have the entire study sample cohort, but maybe you would actually not want to combine blunt and other. And if you decide to exclude a category altogether from your study sample population, then you can't just pretend that they never existed in your study. So if you're making a 2x2 table from a larger table, you have to make a correction, which is what we call the Bonferroni correction, so that you don't just assume that this other group did not exist. So again, we had a 2x3 table, and this was the p-value. And this 2x3 table had 3 pairwise comparisons. Now, we're making a 2x2 table. So we're making it to be a 1 pairwise comparison. So now, to ensure that the p-value is still appropriately considered, we need to divide the p-value by 3 because we had 3 pairwise comparisons and now we have 1. So therefore, for our data to still be significant, the p-value of the 2x2 analysis must be less than 0.01667. And this is what we call the Bonferroni correction. So again, when we've excluded other, and you can see this in the number of total patients that has now been reduced, this is the p-value that's applied. Is it still significant when we just compare penetrating versus blunt? Yes, it is, because this p-value is in fact below 0.01. However, rather than dividing 0.05 by 3, you can times this p-value by 3. So again, it would be 0.001 times 3. So the p-value for this 2x2 pairwise comparison is 0.03, because now we can talk to it against the usual level of significance of 0.05, because you may have various Bonferroni corrections in your manuscript and you don't want to keep going for one. This is the significant level for this next analysis. That is the significant level. What you really want to say is it significant at a level of 5%? So this is the way you get around it. So yes, there is still a significant difference, and you will say that this is the Bonferroni corrected p-value. So then we're going to talk about continuous data. And as I said, when we're looking at continuous versus continuous variables, this is when we talk about our correlations. So we know that our data in this cohort is not normally distributed, so it's non-parametric. So in this case, we will apply a Spearman correlation. So I've just added what I put into Stata. So it's Spearman looking at age versus shock index. This is what it looks like. You can see that there seems to be a negative correlation, and the p-value is certainly significant at 0.007. When we look at age according to arrival heart rate, this all seems to be clustered around a central value and then dispersing from there. We can see from the p-value that, in fact, it is not statistically significant. So not correlated. So I've told you what statistics can do, and really, most importantly, it can enable you to evaluate your hypothesis. But what it can't do is tell you everything. It can only give you probabilistic conclusions, and it cannot indicate clinical significance. But you need statistical significance before you can indicate that there now is a clinical significance. So this is an overview of what we looked at. So what I thought to do also in this presentation while you're here is just briefly touch on sample size, the bare minimum, just so you have some idea how to actually calculate your sample size to know if your study design is appropriate and powered. So just briefly, I'm going to talk about why you should calculate sample size upfront and how to do it with an example. Again, the bare minimum. Why calculate sample size? So one of the pivotal aspects of planning a clinical study is the calculation of the sample size. It's naturally neither practical nor feasible to study the whole population in any study. Hence, a set of participants is selected from the population, which is less in number or size, but adequately represents the population from which it is drawn, so that true inferences about the population can be made from the results obtained. Okay, so the set of individuals will then be known as the sample. So the main aim of a sample size calculation is to determine the number of participants from a population needed to detect a clinically relevant treatment or effect between these groups. Again, we can't study the whole population. So we select participants from the population, which is known as the sample. Okay, so the sample is obviously less in number, but adequately represents the population from which it is drawn. And this is so that true inferences about the population can be made from the results obtained. So in a statistical context, the population is defined as the complete set of people or individuals, the target population. And they are a subset of individuals with specific clinical and demographic characteristics in whom you want to study your intervention. For example, females between the ages of 45 and 60 with systolic blood pressures greater than 140, diastolic greater than 90. And the sample is a further subset of this target population, which we would like to include in the study. Thus, a sample is a portion, piece, or segment that is representative of a whole. So components of sample size calculations. The calculation of an adequate sample size becomes crucial in any clinical study and is the process by which we calculate the optimum number of participants required to be able to arrive at an ethically and scientifically valid result. Generally, the sample size of any study depends on the following, and you would have read this in manuscripts and you would have become acquainted as you investigate sample size yourself. But basically, it depends on the acceptable level of significance, as we saw in our previous examples, which is 5% or a p-value of 0.05 or less. The power of the study is used to calculate the sample size, and a minimum of 80% is accepted globally. An expected effect size the underlying event rate in the population, and the standard deviation in the population. So I will explain by using examples. So this data is from a discovery or pilot study. So basically, we analyzed some cytokines in pancreatic cancer patients versus our control participants. We looked at IL-15, IL-8, and CXCL10. So from our pilot study, you'll see that our control group had 46 patients and our pancreatic cancer group had 85 patients. So this is almost a 2-to-1 ratio. From our pilot data, these were our means and standard deviations for these cytokines, which were significantly different. So now I am designing my larger study to really determine whether these differences truly exist. And therefore, I need to see what number of patients do I actually need to know that there's a true difference. So in Stata, the following commands are used to determine the power and basically estimate the sample size. So in this example, I've used the mean and standard deviation of CXCL10. You'll see that the mean was 1,900, standard deviation of 1,500 versus the control group of 965 and 688. Okay, so again, with an alpha level of 5% and a power of 90%, again, I said 80%, ideally minimum power of a study is 80%, but if we calculate it on a nice high power of 90%, and we use the 2-to-1 ratio as we saw in our pilot study, because we presume that recruitment for our larger study will also be a 2-to-1. Again, the M1 is from our control group, M2 is our pancreatic cancer group, standard deviations as appropriate respectively. And there we see we need an N number of 54 patients. In total, our control group needs 18 and our study group, pancreatic cancer study group, requires 36. Okay, so again, if we calculate it at a power of 80%, you'll see obviously now the sample size is lower. So this is the bare minimum to truly detect a difference for CXCL10. But of course, we have 3 cytokines, not just the one. So if we look at all 3 cytokines, we want to take the one that is obviously going to ensure that all are covered. So we're going to have to go with a larger sample size. And yeah, you see it's IL-15. The power of 90, we will need 159 patients, 53 controls, and 106 pancreatic cancer patients based on our pilot data. So if you have not conducted a pilot study, this is where you can use what is quoted in the literature to determine your sample size. If the inclusion criteria has been similar to what your study design is, and if the study design as a whole really mirrors yours quite closely, then you can use their data to determine sample size for your population. Okay, so yeah, we can see that we're going to have to go with IL-15 to ensure that we see true differences for all 3 cytokines. Again, that was at a power of 90. So what's the absolute bare minimum? If we use a power of 80%, we at the very least need a study population of 120 patients, 40 of whom are control, and 80 pancreatic cancer patients. So I hope that gave you some insight as to how to use either your pilot data or data from the literature to determine sample size. Briefly, what we spoke about. I thank you for your attention. I know it's been rather lengthy, but I truly hope that it has been helpful to you. Thank you so much for listening. Keep well.